Hi guys and welcome to CodeChef Starters 37. As you can see, the contest is still going, but I already solved all problems, and by the way, I got second place. So I decided to record an editorial, sort of. Because CodeChef releases official video editorials, right? But they don't do it for all problems. For example, I'm pretty sure that for these problems there will be no video editorial. And also, they are kind of long. They go over the entirety of problem, which I don't like. I think it is better if I only go over the solution briefly and focus on most important points. Because if you're watching this, then you are probably taking part in this competition yourself, and you just missed one or two key observations. So it's most important to give these observations that you missed instead of discussing the entirety of the problem. So let's jump straight into it. For non-scoreable problems for Div1, these four, they focus only on implementation basics, but they are still good for beginners. So in problem number 1, we wanted to ride a roller coaster. We had some height and we had some height limit, and we just had to check if we can ride it. So obviously this is just one if-else statement, or you can also employ ternary operator in C++ at least. The only tricky point in this problem was that if your height, which is x, is exactly h, then answer is also yes. In second problem, we wanted to transport as many mangoes over a river as possible. The river had a bridge over it with given capacity, and we also had a truck that also had some weight, and mangoes also have some weight. So you want to pack as many mangoes as possible to not exceed the limit. So obviously, once you take limit, right, you already have some weight allocated to your truck. The difference is how many you can transport in mangoes, and because you cannot transport each mango is weighs x kilograms, so you just divide, and C++ conveniently rounds down. In this problem there were no tricky points. In particular, y could not have exceeded z by constraints of the problem. I think it could have made the problem better, in terms of thinking about corner cases, but they decided to exclude it, so whatever. This problem is also possible to solve with binary search, but we will not go into details, because if you can't come up with a mass solution, then it's probably a good thing to do it. In next problem, Chef wanted to buy a laptop. He had 10 different models, and he asked their friends to recommend. He wants to buy the most popular model recommended by his friends. But sometimes he can also be confused if there are multiple equally popular models. So my solution is a bit long for this problem, but nothing extremely smart. We compute frequency map, how many friends recommended each model, and we compute maximum frequency. Then we check how many models have maximum frequency. If there is more than one, then he's confused. Otherwise, we output popular model, the most popular, and how to find the most popular? Well, it's the one that has frequency equal to maximum frequency. So that's it. The code ended up being a bit long, but I hope it's readable enough. Next problem, Inferna. In this problem, we had to defeat an army of n enemies. Each of them had certain health points. We had a weapon that can target enemies individually or all at once. And we were able to select only one of the mods for the entirety of the game. It's actually a good problem if you can switch between the two, but we will not discuss it here. So obviously, because there are only two strategies, we just had to find the time it takes for each of the strategies. For single shot, for targeting enemies individually, each enemy takes hi divided by x rounded up. In C++ we round up like this time. So the total time is just sum. In multi-shot strategy, each enemy takes hi time to defeat and overall time is maximum. So we computed this, how long it takes for each strategy, and then we just take whatever strategy is best. That's it. Now I'm getting into a little bit more interesting problems. Beat the average. Here we had an exam that n students took an exam. They got scores from 0 to m. The average is exactly x. You get an A grade if you score strictly above the average. And you want to maximize the number of students who gets an A grade. So this problem is a little bit tricky, but not really. Like if your average is equal to maximum, then you cannot score more than average. So the answer is just 0. Otherwise, each of the students that receive A grade, they score at least x plus 1. And total sum of grades is n times x, because x is an average and n is the number of students. So this is the total grade, the sum of all grades. Each student takes at least that many, each A grade takes at least that many points. So when you divide and round up, you get the maximum number of A grades possible. It is not hard to show by using discrete continuity that this bound is achievable. Please do so. It's a good exercise. Next problem, maximum or minimum. We had n binary numbers, which are zeros and ones. And by the way, it is an interesting question to solve this problem if AI can go up to, like, let's say 10 to the 30. So like consist of 30 bits. I actually do not know how to solve this problem. But I don't think that it's particularly hard. So there were these n numbers. They are numbers on the blackboard. Alice erases 2 and replaces them by or, which is basically maximum. Bob takes 2 and replaces with and, which is basically minimum. Alice wants to maximize the number remaining after all operations. Bob wants to minimize the number. So basically what they do is Alice, as long as there are zeros, she can remove 1 0 in her operation. And Bob can remove 1 1. So obviously who wins? Well, whoever has less numbers to remove. And in the case of a tie, like Alice has to remove that many numbers. Bob has to remove that many numbers. In the case of a tie, Alice wins, so the answer is 1. And otherwise, if Alice has more operations to do than Bob, then Bob wins and the answer is 0. Now the problem is a very hard name, but not a hard problem. In this operation we had array of even size. Half of the elements were even, half of the elements were odd. What we are allowed to do is to perform these operations. So increase one element by 1 and decrease other element by 1. So first thing to notice is that these operations allow you to perform any transform on the array as long as one invariant is kept intact. The sum of the array must not change. Everything else is achievable by an obvious greedy strategy when we first change first element to whatever it should be, then change second element, etc. And last element will be whatever it should be given the sum constraint. We needed to equalize all odd elements and all even elements. So my submission thinks along the following lines. So first of all, we will have, let's say that k is n over 2. Then we will have k odd elements and k even elements. That's not the same even element by e, the same odd element by o, then k times E plus O is equal to sum. So sum is clearly divisible by k. If it's not, then answer is 0. No. And besides that, the quotient should be equal to some even value plus some odd value, so it should be odd. So we check if quotient is even or there is no divisibility, then the answer is no. Otherwise, the answer is yes. And you can easily prove one possible solution is you change all even elements to 0 and all odd elements you equalize. And because this divisibility happens, you can always show that your greedy strategy that we discussed earlier always works. So this is the entirety of this problem. Then we are getting into interesting problems. In problem 2 min, we needed to partition array into several subsequences and maximize the mean of means. So my solution to this problem goes as follows. I assumed that the optimal strategy is to pick some. Let's actually look. We can look. Let's look at my wrong submission first, because it's educational. So first I assume that optimal strategy is of the following form. We pick some middle element, then all small elements we group together, and all large elements we put into their own sequence. I think there is mathematical proof that why such strategy is sort of optimal. For some reason, I thought that we can perform binary search, but apparently no. So we needed to, and the reason why we cannot perform binary search is because this strategy, the mean value that this strategy gives is a function of middle that is apparently not monotone, or rather this function minus middle is not monotone. So yeah. And the reason why I thought that this strategy works is because like mean of means is the same as giving some weight to each value. If values are small, then you want to give them small weights. If values are big, then you want to give them big weights in order to maximize the resultant sum. Anyway, it turns out that one of such strategies works. Which one? Good question. I don't know which one, but I know that there are n plus 1 different strategies. Namely, like if you take this middle element, you can pick it to be any value, but it does not make sense to pick it something different than our array elements. Because if you have numbers like 10 and 20, your array is 10 and 20, then picking middle equal to 12, to 15, to 20 is the same thing. So it only makes sense to check all array elements. And we can do so by sorting an array and pre-computing prefix sums, because prefix sum allow efficient range sum queries, like so. So one of these strategies, we can loop, now that we have prefix sums of a sorted array. We can check all such strategies, and one of them will be optimal. So we just take maximum value over all such strategies, and it works. I assume that it is not immediately clear to you why this works, but I hope that reasonings I provided makes sense about assigning small weights to small elements and large weights to large elements. Next problem, remove balance. In this problem, we were given a bracket sequence, and we were allowed in one operation to remove any regular substring. We wanted to find the minimum resultant length and also the minimum number of operations to achieve it. Minimum number of removals to achieve it. So what I noticed is, let's keep track of balance as we usually do. If we encounter opening bracket, we increase balance. If we encounter closing bracket, we decrease balance. If balance ever goes below 0, then it means we encountered extra closing bracket. We cannot get rid out of this bracket, so we can immediately increase the length of the resultant string, because there is no way we are getting rid of this bracket. Besides it, if there was an non-empty substring before we encountered this closing bracket, then we also need to perform one operation to remove that substring. So after all of these operations are done, we maybe have some non-empty part. If this non-empty part has non-zero balance, if it has zero balance, then we can remove it in one operation. Otherwise, we will reverse the string, change all brackets, and basically apply the same algorithm in reverse. And I claim that by this point, result will be empty. It's not particularly difficult to understand why. Like if you just write down your balances, then you will see why this works. Please do. It's a good exercise once again. So yeah, just applying algorithm forward and backward was enough to get accepted. As you can see, this problem has quite some test cases, but apparently this works because we are easily clearing all test cases. Next problem is actually a big ripoff of AdCoder problem. ARC137, problem D. It is even titled the same way. In both problems we have an array and we apply prefix XOR operations to it multiple times. So in first operation, new array B becomes prefix XOR of A, in second iteration, new array C becomes prefix XOR of B, etc. And we need to learn how to quickly find what will be the value of access element after k operations. This constraint clearly shows that we need to answer queries in logarithmic time. So if you read the editorial for this problem, then you know that we can compute values bit by bit, or actually because in this problem, initial array is very specific. It's identity array. So we already know that we are supposed to find the answer in logarithmic time. So let's learn how to find the ith bit of the answer. Clearly bits are independent, so may as well find the answer bit by bit. Now, if you read these editorials, you understand that bit appears or does not appear depending on some binomial coefficient, which you can simplify using Lucas theorem, which is a great fact from mathematics. It allows you to quickly compute binomial coefficients modulo some prime. Number 2 is a prime, as you may know. So this expression is very simple for modulo 2. Obviously, the answer is either 0 or 1, and the answer is 0 if and only if there is a digit I, such that like mi is 1 and mi is 0 and ni is 1. So you're trying to choose one element out of 0. There are obviously no ways to do it. So if one of the multipliers is 0, then entire product is 0. So that's the only case when your binomial coefficient can be 0 modulo 2. To paraphrase, your binomial coefficient is 1 if and only if n is a submask of m. And if you run this process for small values of x and k. For example, I picked x from 0 to 16 and k from 0 to 16 and looked at 4 bits. I was able to notice that values that they are mostly almost the same as the numbers in this binomial coefficient. They are almost the same as x and k, except that row is 2 to the power of bit greater and column is 2 to the power of bit smaller. I really encourage you to write brute force for small values of x and k, and you will see by yourself the binomial, that Pascal triangle modulo 2 appears, but it is shifted by exactly these numbers. So Lucas theorem allows us to quickly compute Pascal triangle modulo 2, but our Pascal triangle is shifted by this vector, plus 2 to the power of bit, minus 2 to the power of bit. And we just check if row is submask of sum. This can be done in C++ this way. And also column has to be non-negative because like here we subtracted, so small little detail. So this allows us to find if given bit appears in answer. For each bit the shift is its own, so maybe this what made this problem difficult for others. But if you look bit by bit, then you clearly realize that something like this happens. So yeah, then you are able to see the pattern, especially if you've seen the add coder problem, it should click very easily for you. So yeah. In case you have a difficult time understanding the solution, please refer to the editorial for add coder problem. And I hope you learned something new. I cannot say that I learned something new, but yeah, it shows that participating in many contests definitely helps because a similar problem can reappear. So please participate in more contests and watch more editorials that I make. So yeah, thanks everyone for watching, and I'll see you guys tomorrow on Thursday with yet another Codeforces Div3 round. Yes, we have back-to-back Div3 rounds. Very unusual, but this is the case. Thanks guys, bye bye.